Okay, so we have really two equations for heat. And the thing I want to point out for today's assignment that's really important to remember is that we are really focusing only on heat required for a temperature change. Things get more complicated if there's also a phase change required. So there will be practice in 404 that some of you may have already looked at that will really focus in on the calculations for heat needed for a phase change. But we're gonna talk about them for a second here, but we're not going to really calculate them now because we really want to kind of hone in on what we need for the lab today. So thank you for put that up on the screen. Q equals MC delta T is really going to be our focus for today, and we're going to talk about what that is and how it helps us here. What is the equation? Oh, there you go. Perfect timing. Very simple as far as the math goes. We're just going to take the mass times some specific value that's probably going to be given to us. So it's going to be a series of multiplying when we're looking for how much heat is needed for a phase change. But like I said, I'm going to give you some time to really work on 404 if you haven't gotten to that. And then we can kind of circle back and talk about that calculation more if we need to. So for now, what we want to focus on is what is this Q equals MC delta T really telling us? If anybody wants to take the mic, can anybody tell me what each of those variables stands for? And raise your hand if you'd like to take the mic. I want to see them typing. Typing's okay too. I'd like to hear your voices, but I'll take typing. Let's see here. Sierra's got Q. So, and I'm happy you say that entire phrase, quantity of heat. That's a nice reminder there because you think, well, H would make more sense here, but we have H for something else, and you know, there's only so many letters in the alphabet. So Q is for the quantity of heat. It's how much heat those materials are releasing or gaining. And then M, of course, is mass. Nothing too new with that one. And then delta T is the change in temperature. So that delta is back. That's the Greek letter delta, and it always stands for change. So we're circling back to that. And then what about C? C is probably the newest variable. That's maybe not talked about oh so much in normal conversation. Yes, specific heat capacity. Thank you, Helga. Do you want to add anything to that list?
Well, I wasn't about to say that C equals the specific heat capacity.
Thank you. Yep. Sierra beat you to it in their typing. So that's probably the newest term of all of these. Those of you that have taken biology with us, I know for certain have come across that term specific heat capacity because in biology there is a lesson about the properties of water, and one of those is specific heat capacity that is touched on there. So if you maybe dig into your long-term recall and think back to the water lessons in biology, that would be a nice connection there. And today I added a crash course video where I don't know his name, but he talks about all the properties of water. And if you fast forward to the last two, those are really the physics properties that we're, Hank, that we're going to focus on. So if you do take time to watch a video, I think it's a longer one, it's like 11 minutes. The beginning's very funny and entertaining, and then at the end, 9 and 10, I think is what he's numbered them, are, yes, they're really good. So that's a nice one to really, I think more so appreciate how special water really is. I think a lot of us might take water for granted. I think almost everyone. Anyways, let's move on. And we're not going to go over each of these terms in deep detail right now, but the one that I do want to stress here that's really important for the lab today is thermal equilibrium. And I think that might really require microphones. So can somebody give me kind of their version of the definition to thermal equilibrium? What would that really mean? Sam, go ahead.
Hello? Can you hear me? Okay.
Yes, we can hear you.
Thermal equilibrium is when two substances have reached they both reached the same temperature, basically, because the heat has transferred from the thing that had a higher temperature to the thing that had a lower temperature.
Excellent. Thank you. And so one example that I believe I included in one of the playlist videos for last week would be a thermometer. I know a lot of us probably don't have the old school, definitely not the mercury-filled thermometer, but a liquid-filled thermometer. And what do we see happening as we maybe, let's say, have a fever and we put that thermometer in our mouth? We're seeing that liquid rise. We're really looking at thermal equilibrium occurring. When that liquid stops rising is when the liquid inside is the same at temperature as the inside of your mouth, and we can get that reading. So technically, we're really not even measuring temperature. Temperature is kind of an assigned value, and we're really waiting for that thermal equilibrium to happen. So that is great, and I'm happy to hear you say that the energy transfers from that hotter to the cooler. It's really kind of like a game of bumper cars, right? Those molecules for that hotter object are moving faster, and they're knocking into that cooler object's molecules, and it's kind of that chain reaction. Everything starts transferring. That energy from the faster molecules is passing to the slower, and eventually everybody's bouncing around at that same speed. Very good. Lots of great connections there. So let's dive into, and actually I'm going to hold off on the 404 practice because we're going to see that in the lab. So let's jump into the lab so we can get a better feel for a real life scenario. So first we just need to be familiar with the variables that we're going to come across here. So Sam had mentioned an object. Oh, and we can put your hand down, Sam. Thank you. Okay. So what we are focusing on is similar to what Sam just mentioned. We have a hotter material pushing that energy away from itself into a cooler. So cooler material. So what we have in this example is a certain mass of material. You can see that little guy right there in the container, and set at a certain temperature. The water is set at a cooler temperature. And we'll see thermal equilibrium happen over time. So what I'd like you guys to do, and this might make the page turn really ugly, but I want you to draw arrows to where each of these variables are in this little experiment here. So for example, I'm going to do one of them. Let's say I want to locate the mass of the metal. Well, the metal is listed at the top here, so this right here would be the mass of the metal. Let's look for the mass of the water, the original temperature of the metal, the original temperature of the water, and the final temperature. It's looking pretty good. It's like organized chaos. I was hoping to see the lines all go in a similar direction. That's what we're interested in here. So I'm thinking maybe this line right here, which I'm not sure I can necessarily delete, but I'm going to put a little X on it. This one right here I think might be going the wrong way. The rest look pretty good. So I think it's probably pretty natural to pick out where all this data is, and you're going to do that same thing in your own experiment. So we can take a break from the lines. Good job with the line tool. You guys are competent in drawing lines, or, I don't know, not such straight lines, but that's okay. Let's focus on the questions here now. So what will happen to the water? And we can kind of see that from the data already. What happened to the water? If this is, where'd it go? Here's the original temperature of the water over here, but then the final temperature of the system was over here. What happened? Naturally, that water has to warm up, right? It was cooler, so it's gaining heat. So that's really how we want to kind of relate it as we move into an equation. The water is gaining heat. What will happen to the mystery mass? Well, of course, it's losing that heat, as Sam mentioned earlier, Betty. And we really have to wait for this experiment to happen, right? It's not instantly going to reach thermal equilibrium. It's going to take some time. So we, if we had this set up, could kind of graph temperature versus time and see that change progress. And then, this is probably the most important question here, letter C. How do these changes compare? So we know the metal, the water is gaining heat. The metal is losing heat. How do they compare? Oh, Sam, great point. Absolutely. We can see that temperature differentiation, right? Barely any, because water has such a high specific heat. Right, and Helga's got it. Look at Helga's comment in the chat box. That is critical to doing this lab. And I've found in previous years, students kind of miss the boat on that point, and then they're asking questions that they probably should have been able to answer. They reach thermal equilibrium, so it has to be that even exchange. And this term calorimeter is, I'd say probably even more so in the chemistry category, important. It's telling us that this container is insulated and there really isn't any energy escaping outside of the experiment. So we can say conservation of thermal energy will occur here because the heat that's lost by the metal is in turn gained by the water. And that'll be important to your calculations. Does anybody have any questions on the lab setup?